but the technical not coming now. So we would like to start and wait to start.
To wait.
No, I think we would like to start.
We like.
Yeah. I would like to give your big hand to welcome Dr. Roger K.
Thanks very much. I'm a bit sorry I can't give this talk in time, but I'll try and speak slowly. Okay, so it might take a little bit longer, but please think of it as informal. If you want to interrupt and ask questions, that's fine. Okay. So, for many years now, I've been working with my colleague from the Naval Postgraduate School in Monterey, Michael Montgomery. And about 8 years ago, this very young, very bright student who came to work with me, Gerard Kilroy, who was mentioned before, and both Gerard and Michael have had a lot of input into this research I'm going to talk about. In fact, Gerard did all the calculations I'll talk about. So the motivation for this talk is, first of all, to forecast tropical cyclones or to determine what the changes might be if there is global warming. We need to have a conceptual model of how tropical cyclones work. If somebody from the public says, how do tropical cyclones work? What would you tell them? That's something that people might ask. So what do we know? What do we understand about the basic processes? So this basic question is, how do tropical cyclones form? How do they intensify? What are the physical processes of intensification? How do they decay? I'm not going to talk about the decay so much today. Another question is, why do they sometimes intensify rapidly? And so then you ask yourselves, well, what conceptual models are available? If I look in the textbooks, if I look in the literature, what do we understand? What are the theories available? Now, about 12 years ago, 13 years ago, Mike Montgomery came to visit me in Munich. And our plan was to start to work on a book on tropical cyclones, essentially the dynamics. And we rented a little holiday house in the mountains, and we spent a week together talking about what we understood. And after about 4 days, we decided we didn't really understand anything very much. And since then, we have been working steadily, asking questions and trying to build up ideas about how tropical cyclones work. And first of all, we did a few years ago, we started to write a review of the literature and essentially what conceptual models are available. If I look in the literature, what will I find out? And we wrote an article in the Australian Meteorological and Oceanographical Society journal in 2014, where we compared the different ideas about how tropical cyclones work. More recently, we've updated this review. We have a paper in 2017, and I'll tell you about that later. So, what have people understood in the past? One of the early and very influential, important studies was that of Vic Uyama, who was Japanese, who worked a long time at the Hurricane Research Division in the US. And he wrote this paper in 1969 in the Journal of Atmospheric Sciences. And he explained, he proposed a theory which we now call the classical paradigm, or the classical theory. I will refer to that paradigm. I will explain what that is in this lecture. But in the mid-1980s, Kerry Emanuel, who at that time was a young researcher at Massachusetts Institute of Technology in the US, proposed a model for a steady-state hurricane. And later on, in the mid-90s, he extended this model to a developing storm, to provide a theory for how storms develop. And this is often referred to, this theory is often referred to as the Wishy paradigm, or the Wishy theory. And Wishy stands for wind-induced surface heat exchange. And the idea is that where the winds are very strong near the center of a storm, the surface moisture fluxes will be strong, and that there will be a feedback between the surface fluxes of moisture and the winds. And I don't have time to explain this feedback in detail, but you can read about that in our review paper, for example. But in a series of papers, including some rather recent ones, we've shown that this feedback mechanism is not necessary. You don't need to invoke this feedback between the surface fluxes and the wind speeds to explain intensification. So over the years, we've developed what we refer to as the rotating convection paradigm. And that's what I will talk about today. And this paradigm is really an extension of Uyama's paradigm, but with some additions. And I'd like to try to explain this to you today. What's nice about this new paradigm, in our view, is that it provides a unified theory for both cyclogenesis and intensification. As you'll know, Chai, the WMO workshops on tropical cyclones, which they have every 4 years, they have a session on intensification, and they have a session on genesis. And intensification and genesis were always treated as separate things, different things. First of all, you had genesis by some processes, and then you had intensification by some other processes. What we believe, and I will try and convince you today, is that it's just a continuum, that it's all one process. So we don't need to talk about genesis and intensification really as separate physical processes. It's all the same. Well, a few things that probably most people here know about the structure of a tropical cyclone. Essentially, a mature tropical cyclone is a large, convectively rotating system. The strongest winds are at quite low levels near the surface, and I will explain to you why that is so. So the winds here are rotating cyclonically, but superimposed on this cyclonic rotation is what we call a secondary circulation. So the air is coming into the system at low levels. It goes up into these large eye wall clouds surrounding a cloud-free or largely cloud-free eye, and then it comes out in the upper troposphere and there's a lot of cirrus cloud, of course, marking this airflow. And when we look from satellite, we mostly see this cirrus cloud. And then outside the main eye wall, the eye wall is composed of sort of thunderstorms, deep, very deep thunderstorms, like a ring of these storms. Surrounding the, or outside of the eye wall, there is often a clear area, and then there are these rain bands further out from the storm. That's the typical structure. And this is a very early numerical simulation by Ricanthes, just emphasizing that the air is spiraling in the boundary layer, in the friction layer near the surface. It then spirals up, and then it spirals out above, and becomes anticyclonic in the outflow. I'll explain to you why it becomes anticyclonic also. These are just two nice pictures I found from Hurricane Florence last year, which show that the eye has a lot of structure inside it, and although the winds near the surface are calm, the eye wall itself tends to be an area of high instability, and there are often little vortices in the eye itself. So how do we go about understanding these systems? How do we understand how they work? And I want to talk about this thought experiment. Okay, so it's basically, we use a numerical model, and we take, as part of this thought experiment, a vortex which has some structure. We're going to do a numerical simulation, an idealized numerical simulation. And we're going to, it's like doing a weather forecast, but we're going to do the weather forecast for a weakly rotating flow, which we specify as an initial condition. And this initial condition is a tangential wind field, which is a function of radius from the center of some domain. It's a function of height, and we just prescribe that. We say what that is. We give this and we calculate a temperature field which is in balance with this vortex. The maximum tangential wind that we take is 5 meters per second, which is relatively weak. Okay. So we're going to take a very weak initial vortex. It's initially cloud-free, it's initially axisymmetric. And we sit this vortex over a sea, which has a typical tropical value. We take 29 degrees Celsius. And we also need to have an environmental sounding for the simulation. And we take, in these calculations, we take a sounding from some data that we had for a developing storm that were obtained during a field experiment in 2010. So we had lots of measurements in and around the storm before it had developed properly. And we use that sounding. And so we specify the temperature and humidity as a function of height, and we specify the surface pressure. So this is an idealized experiment to study how a tropical cyclone forms and how it intensifies. Okay? This is our starting point. The calculations, this study was published in the Quarterly Journal of the Royal Meteorological Society last year. The calculations were done using a model from the National Centre for Atmospheric Research. It's not the WRF model, it's George Bryan's cloud model. It has the nice advantage that the treatment of moist processes in the model is very accurate compared with WRF or other models. And we have simple physics in these calculations. In other words, we treat clouds as only being warm, having warm rain processes. So the clouds don't develop ice. But I'll talk later about what ice does. So we use this CM1 model. We have a grid spacing in the horizontal of only 500 meters. So very high resolution calculation. And we have 40 levels in the vertical up to 25 kilometers. And we have a stretched grid in the model. So we don't have nested domains, we just stretch the grid. But the inner part of the domain, the inner 300 kilometers, we have a grid spacing of 500 meters. So very high resolution compared with typical calculations. So then the question is, okay, we start the model off with this initial condition. What happens? And how can we understand how tropical cyclones form from this experiment, this idealized thought experiment or idealized simulation? Now, before I can answer that question, I want to talk about some basic physical principles for understanding vortices. Probably this is one of the more important ones, and that is the idea of the conservation of a quantity, n, which we call the absolute angular momentum. I think most of you know about angular momentum. So the idea is we have air parcels moving around in a circuit. And if we think about one air parcel, its absolute angular momentum is the tangential velocity, that's V, times the radius of that parcel from the axis of rotation, plus a contribution from the Earth's background rotation. This contribution here is why we refer to absolute. So we're in a frame of reference moving relative to the Earth, and so the Earth contributes to the absolute, to the angular momentum. And it turns out that this quantity m, if there's no friction, so that's if we're away from the surface, this quantity m is approximately conserved for an air parcel. That means every air parcel, if we know its value of m, initially, that air parcel keeps this value of m. And that means if an air parcel moves to a different radius, we can calculate the change in its tangential wing. For example, we can solve this equation for the tangential wing V, and we get this formula here. And what this tells us is that if the air parcel moves inwards radially, so if it goes in a trajectory like this, then R will get smaller, M will stay the same, okay, M is conserved for that air parcel, always stays the same. So R gets smaller, this term gets bigger, this term gets smaller, but this is negative. And so both these terms, if R gets smaller, they both contribute to an increase in V. So, principle is very simple. If we can get air parcels to move inwards, they will spin faster. Okay? And also, if air parcels move outwards, then R will get bigger, this will get smaller, this will get bigger and more negative, and so V will decrease. So if air parcels move out, they will move more slowly. Okay? This is very important. This is the central idea for how vortices spin up and spin down. So the conclusion here is that spin up requires radial convergence. We only get spin up if we can draw air parcels in towards the axis. And if you try to explain how hurricanes work, you need to have this principle in the back of your mind. It has to be part of your explanation. Now, I want to talk about friction. And so, I'm moving away from tropical cyclones, and I want to talk about air flow past an aeroplane's wing. Okay? We know what, if we know some basic fluid dynamics, we know that as air flows past the wing, it slows down when it gets near the surface. It gets slowed down by friction on the wing. Okay? Let me see if I can animate this. Oh. No. How do I animate that? There should be a little thing down here.
Animation.
Can you click on that?
Animation.
Yes, there we go. There we go. So, you see, the air up here just deforms a little bit, but has the same speed as over here, but the air near the wing is slowed down. We have a profile of flow like here, where the air close to the wing is flowing much more slowly. Okay? That's the effect of friction. Okay? You're sure familiar with that. We can simplify this. You can imagine the wing is a flat plate, and we can think of an airstream approaching the wing, and friction starts to slow down the air when it meets the plate. And we end up with a profile of flow like this, where the flow near the plate is much smaller than the flow above the plate. So we have what we call a boundary layer here, and the boundary layer gets thicker and thicker as more and more air is slowed down by friction near the surface. Now, the interesting thing about this is the air near the surface is slowed down, slower than it is above. So then the next question is, how do we explain the idea that in a tropical cyclone, the maximum winds are in the layer with friction? Okay, that's not something we would expect from this idea. So that's one thing I want to explain. So let's look at the effect of friction in a vortical flow, in a flow that's rotating. Now, in a vortical flow in a low pressure system, we have an approximate balance of forces. In a rapidly rotating vortex, we have a pressure gradient, a radial pressure gradient, which is inwards towards the center of the vortex. And this pressure gradient is approximately balanced by the Coriolis and centrifugal forces acting on the air parcel, and they both point outwards for a cyclonic vortex. And they're roughly equal, not quite, but roughly. But as we come down to the boundary, the centrifugal forces and Coriolis forces, these are both reduced by friction, because the centrifugal force depends on the velocity squared, and the Coriolis force depends on the velocity. So these forces are reduced as we come down near to the sea surface, but the pressure gradient doesn't change very much. You can show that by a scale analysis of the equation. So what we end up with is that we have an imbalance of forces in the layer of friction, and that imbalance of forces produces flow towards the center of the vortex, near the surface. And so essentially we have a secondary circulation. There is inflow induced by friction near the surface, and we have outflow above the layer of friction. So we have this secondary circulation induced by friction. You can do a nice little experiment. If you have a coffee pot and you fill it with water and you take some tea leaves and you give the water a big stir, so you make a vortex, and you put some tea leaves in, and after about 30 seconds or a minute, the tea leaves will be in a nice little pile near the center of the can. And what happens is that as soon as we create the vortex, we generate inflow near the boundary because of friction and outflow above. Remember that where above the friction layer, the absolute angular momentum is approximately constant because there's no friction there, we're above the friction there. And if the air is moving out above the friction there, or if the water is moving out, the air particles are slowing down. And the reason the water in the tank, when you stir it and make this vortex, the reason that the vortex slows down is not because the friction is acting to slow down the air and that effect is just transmitting from the surface to the interior. It's because friction generates this secondary circulation, and in the region where the fluid is moving outwards, the air particles are conserving their absolute angular momentum, and therefore they're spinning more slowly. And that process associated with the secondary circulation is much faster than if friction was just acting by itself. It's an indirect of friction for spinning down. So in summary, how do vortices spin down? We need to know how vortices spin down before we can perhaps explain how they spin up. So if we have a friction near the surface, we have what's called a boundary layer or a frictional layer. We have inflow produced by the breakdown in the balance of forces due to the friction. That generates the secondary circulation, and the tangential velocity of the main part of the vortex spins down because the fluid particles, air or water, are moving outwards and conserving their absolute angular momentum. And we saw from that basic principle, if fluid particles move outwards, they spin more slowly. Okay. So with friction, vortices will tend to spin down. So how can we get a vortex to spin up? How can we explain the spin up of a tropical cyclone? Clearly, we have to have air moving inwards. Now, we say, well, the air's moving inwards in the boundary layer, but really, the absolute angular momentum is not conserved in the boundary layer, so we can't apply our argument with absolute angular momentum for the boundary layer. So we have to think of some way of producing convergence. The only way we can think of, in reality, is deep convection. Because what deep convection does is deep convection takes air from the lower troposphere and carries it up into the upper troposphere and then pushes it outwards. Okay. So deep convection can draw air inwards in the lower troposphere, even above the frictional boundary layer, because that's where we need to get the air to move inwards. Friction will tend to move the air outwards, and so to get spin up, we must pull the air inwards at a rate which is sufficient to overcome the effect of friction, which would make it go outwards. So let's now think about our model. Let's go back to our conceptual model and think about what happens in the model. When we start this experiment from time zero, so we start our forecast at time zero, there are fluxes of moisture develop near the surface. We also switch on friction. friction is switched on at this initial instant. Friction produces this inflow near the surface, as in the coffee pot, and so the moisture is coming from the sea surface. The moisture flux is strongest where the winds are strongest, and in our case, our Vmax here is at a radius of 100 kilometers from the center. So we have these moisture fluxes. We have some convergence of moisture in the boundary layer. What that does is it lifts, the boundary layer gets thicker, the air in the boundary layer is lifted and becomes unstable. And so eventually we overcome the initial convective inhibition, the initial sin in the sounding, and convection starts in this inner region. So I want to show you a movie of that. Can you click on this thing here? This is a domain, it's a square domain. This is just the inner part of the domain. So it's 600 kilometers across. And the time is up here. That should change when it's moving. Can we get it to? Maybe you have to click some. There we go. So I'm showing you contours of vertical velocity in this simulation, greater than 1 meter per second. These show you where the deep clouds are. And initially nothing much happens, and then clouds start to form. And the clouds form in a ring to begin with. That's an artificial part of the experiment, and this ring moves outwards, because initially we produce a gravity wave. But this part's more realistic, this inner part. Because from here we have a collection of clouds, and these clouds are drawing air inwards in the lower troposphere. They're producing convergence. And you see that it's very asymmetric to begin with, but clouds start to form near the center of the circulation, and now we start to get organization, and we start to see what looks like a developing island. It's very asymmetric the whole time, really. It's not a symmetric process. So I can stop that there. Now we have turns out a rather intense vortex. Can we, oh, I can do this. Now, there are ways of understanding this flow. I want to talk about the vorticity perspective first, and then I'll talk about an angular momentum perspective. You all know about relative vorticity. Relative vorticity is a measure of the local rotation rate of a fluid. And the relative vorticity, or the vertical component of relative vorticity, is just twice the local angular velocity. The absolute vorticity is defined as the local relative vorticity plus the planetary vorticity, which I call F. Now, if we, in a vorticity perspective, if we have horizontal convergence, then little elements of fluid will get compressed in the horizontal and stretched in the vertical. And when little elements get stretched in the vertical, their rotation increases. And in contrast to that, if we have divergence, then the initial element will get flattened and will get broader, and it will spin more slowly. And so, in essence, this is just to show that if we have vertical stretching, we get faster rotation. If we have vertical shrinking, we get slower rotation. So what do clouds do? This is the essence of this rotating convection paradigm, or a way of thinking of the intensification of storms, which we've seen is very asymmetric. Now what happens is when a cloud develops, the stretching produced by the cloud updraft increases the vorticity locally, just by the process I was talking about. So each little cloud is stretching vorticity and increasing the local rotation, the local vorticity. Now, there is a theorem which you probably, many of you don't remember, but if you think back to your mathematics days, there's a theorem which says if we take a circuit in a fluid like this, a circuit C, we can calculate the integral of the velocity around this circuit, that's this quantity here, and that's equal to the area integral of the vorticity. So if we know what the vorticity is in some region, we can calculate the velocity around the circuit, that region. And so if we can draw vorticity into a circuit, if we can increase the vorticity inside any circuit, then we can get the mean tangential wind around that circuit to increase. This is a similar idea to angular momentum, but in a vorticity perspective. And this viewpoint has advantages because angular momentum is very useful when the flow is axisymmetric, but if it's not axisymmetric, it's perhaps better to think in terms of vorticity. So the idea is that these clouds are actually producing vorticity locally, but they're also drawing air in towards them. So on a larger scale than the clouds are drawing air in the lower troposphere and pushing that air into the upper troposphere. And so if they're drawing air in, they're drawing vorticity into circuits and in the lower troposphere, and that's going to increase the tangential wind around the circuit, the mean tangential wind. So that's the idea behind this rotating convection paradigm. The clouds themselves amplify the vorticity, and that vorticity and the overturning circulation they produce draws the vorticity in towards the center. Now let's go back to our experiment. Remember, we started with a very weak vortex. The maximum tangential wind was only 5 meters per second at a radius of 100 kilometers. Now, we can plot the tangential wind azimutally averaged as a function of time. And it looks like this. We see in the early stages, the azimutally averaged tangential wind doesn't increase until about nearly 2 days. And then the vortex rapidly begins to increase. We might say that this is the genesis point, somewhere around here. Depends how you define genesis. I think the forecasters use 17 meters per second, so they might put genesis in somewhere in this region here. This is the total wind anywhere in the maximum wind. The maximum total wind anywhere in the domain. This starts to increase earlier because once this convection starts, the convection locally amplifies the wind near the convection. So we see an increase of the local wind first, but the azimuthal average wind just steadily gets bigger, but not a lot, before it suddenly takes off, suddenly increases. This is the radius of the maximum tangential wind. And we start with 100 kilometers, and you see about this time that the vortex develops, the radius of the maximum tangential wind decreases very sharply. So we want to really try and understand what's going on around here. We might call this the genesis point, or the time when intensification really starts. So let me roll on. I'm going to show you these fields here. These plots show the tangential wind at, or the wind vectors at a height of 1 kilometer. Okay, so just above the friction layer. And this is the time. So that's at this time, about 42 hours is in here. This is before not a lot has happened. These are regions of enhanced vorticity. The vorticity has this color code here. So we've got negative vorticity here, positive vorticity here, some areas of stronger vorticity. Now those areas of stronger vorticity are where the clouds have been stretching the local background vorticity. The blue contours here are the contours of 1 meter per second vertical velocity at a height of 2 kilometers. So that shows you where the base of the clouds are. And the yellow is the 1 meter per second contour at a height of 6 kilometers. So that shows you where deep convective clouds exist. So you see some of the regions of strong vorticity are associated with strong updrafts at this time. Other patches of vorticity were produced by previous clouds that have decayed. When clouds stretch vorticity, the clouds may decay, but the vorticity stays there. Okay? When the clouds decay, the vorticity still remains, and so we have patches of enhanced vorticity in here which don't have any clouds with them. So that's at 42 hours. This is at 45 hours. Just in here, this is about the time that the vortex starts to intensify. Look at all the organization of the convection, of the deep convection that's taken place in just 3 hours. 3 hours between here and here. There's just a few patches of deep convection in the domain. Now, a lot of this convection has a lot of the convection has intensified, it's become more organized, and the vorticity associated with it has become more organized. Okay. This is before you see a huge change in the wind speed. This is all at 45 hours. This is in here. Now, if you look at radar pictures of tropical cyclones trying to form, you see this kind of thing. Let's go a little bit further. I should point out that the maximum wind speed here, anywhere in the domain, the maximum tangential wind, azimuth, the average tangential wind speed is only 14 meters per second. Here it's actually a little bit weaker. So we're only talking about relatively weak winds between here and here. If we go to 46 hours, just before this point, we only have 15 meters per second again. A lot more. It's now starting to get really organized with convection near the center of the circulation. And now we're getting a monopole of vorticity near the center of circulation. And only 1 hour later, 2 hours later, 48 hours, which is about this point here, there's been a tremendous organization. The maximum winds are only 16 meters per second in here, but the convection and the vorticity have really organized tremendously. And we've got a lot of convection near the center of circulation. Now, if you think about our basic principle, that if we can draw air in close to the center, we can get large spin-up because of this 1/r. And so a very favorable situation to get development is to have convection near the center of a circulation region, because that is able to draw air in 2 small radii, and then therefore, according to our principle of angular momentum, we can get large spin-up. I want to show you a movie of this. So maybe you could click on that. We start at 36 hours, which was when not much was happening. These are the isolines of pressure. These are the isobars, surface isobars. They don't show anything much at the moment. So we've got deep convection in here. We've got a little bit of deep convection in the center. That deep convection has enhanced vorticity with it. Some more convection forming out here. Enhanced vorticity with deep convection. Here's some remaining vorticity from previous convection. Deep convection here. This little patch of vorticity. We're now at 40 hours. So not a lot's happening. The vortex, you see the pressure is getting a little bit lower, but not a lot happening. Quite a bit of convection near the circulation center in here, and that convection tends to have enhanced vorticity with it. Now we're getting a nice little patch of vorticity in there. It's quite complicated. You have to look at this a lot and study it and think what's going on. Now it's 45 hours, and now we're getting this organization. And now it's ready to go. Okay? We've got this big core of positive vorticity near the center. And we've got a lot of convection, which is becoming organized near the center of circulation. Look, it's trying to form an eyeball in here. This is 48 hours. This is a contour of 1 meter per second, and it's winding around the system. Very asymmetric. You can see now the organization. We've got a big monopole of vorticity. And the convection is trying to get organized in a ring, but it's not properly organized at this stage. Maximum wind speed is 25 meters per second. You see more and more contours of surface pressure now. The system is deepening quite rapidly. You see more contours appearing near the center. The arrows are getting bigger. We're now up to hurricane strength, 35 meters per second. We've got sort of rain band in here, wrapping around, trying to form an eye. Getting a nice big monopole of vorticity in the center and some spiral bands of vorticity. And now we've got a really strong vortex. Well, reasonably strong. Marginal hurricane strength at the moment, yes. And that just keeps going.
What is the dash line?
The dash lines in here,
Yeah.
oh, that's just the boundary between negative and positive. So these regions of here are negative vorticity. So it's that boundary there. So just negative values. So you see we've got a lot of negative vorticity in the outer part here, but we've really only got positive vorticity near the center. Okay, let me move on. So how do we make sense of this? If you look at this, it's very, very complicated. Okay? But this is a bit like nature. It's very complicated. So how can we make sense? Well, what we could do, if there's a bit of distortion here, this should look like a circle. So what we can do is we can choose a vortex center here. And I think we chose the vortex center as the minimum pressure, maybe minimum surface pressure for these experiments. We can choose a center, and then we choose a ring around the center, and we calculate an average around this ring. So any quantity, we can do an azimuthal average about a ring. And then we can just plot these azimuthal averages in a height and radius cross-section. So just as we would if we had an axisymmetric flow, we wouldn't need to look at all this complication. So this is the essence of Vic Uyama's classical paradigm for intensification. So Uyama's idea was this, that if we have some clouds, I mean, I've drawn this as a single cloud, but this is intended to mean a whole group of clouds in the early stages, but in the later stages we may have an eye there. So Uyama's idea was that the clouds draw air in above the friction layer, and because the absolute angular momentum is materially conserved, that means it stays constant for an air parcel that's spiraling inwards. If the air parcel is moving inwards, then an M is staying the same, and then its radius is getting smaller, so its tangential wind speed is increasing. Okay? That's the basic idea. Now, M is not materially conserved in the boundary layer, in the friction layer because friction is reducing the tangential wind, and the tangential wind depends on air. So, in Uyama's time, it was the role of this frictional inflow. It was recognised that there will be inflow in the friction layer, and the inflow was seen to be important because it helped to keep the thunderstorms in this inner region supplied with moisture. Normally clouds will kill themselves because they produce downdrafts and they remove a lot of the moisture from near the surface. So this moisture has to be replaced, and that moisture gets replaced from the fluxes of the sea surface, the moisture fluxes in this region, and that moisture gets transported inwards to keep the clouds going. That was the basic idea how tropical cyclones work, that was articulated by Uyama in 1969. Some years ago, we proposed an addition to this idea because, as I mentioned before, the maximum tangential winds in a tropical cyclone are found in the layer of friction. And I showed you that if we think about flow over an aeroplane wing, the air in the friction layer is flowing less rapidly than air above. So how do we get the maximum tangential winds in the friction layer? Well, what we realized was that this formula works also in the boundary layer, but in the boundary layer, in the friction layer, M is not conserved. M is reduced by friction. Okay? But if we have strong inflow in the boundary layer, it may be that M is not reduced as rapidly as the air parcel is moving inwards. So if M decreases at a slower rate than R, this will still get bigger. Okay? Now, we can't say whether that is true or not. We can just make that as a plausible possibility. But in fact, we can show that that is what happens. So that as air parcels, where they're converging rapidly, the M is not being reduced as much as the change in the radius as the air parcel is moving inwards. So this term can still get bigger. And so in a vortex, we can have the maximum tangential winds in this shallow inflow layer that's feeding the clouds. So this inflow is not just important for supplying the clouds with moisture, it has a dynamical role in producing the strongest winds in the friction layer near to the surface in this inner core region. And of course those maximum winds near the surface are going to increase the fluxes of moisture. So it's this was an addition to this classical mechanism. Now, you may like to think a bit more about the absolute angular momentum, because we've seen it's an important quantity. Over much of the vortex, it's approximately conserved. So the question is, well, what are these angular momentum? What's the distribution of angular momentum look like in the initial vortex?